All right, so we are doing Unit 1 Dynamics, Lesson 10, Newton's 3 laws. So we are going over all 3 laws in one lesson, because it is a review from what we've learned in grade 11. So Newton's first law is the law of inertia. Okay, inertia is just an object's tendency to avoid any change in its motion, right? So inertia resists changes in motion. Now, it is true that objects with a lot of mass have a lot of inertia, but be careful to say that inertia is mass because it's not. Okay, go to the next slide here. Okay, inertia is directly related to an object's mass, so it is true that the more mass an object has, the greater its inertia is, but mass is not inertia. Mass simply has inertia. Okay, so be careful to not distinguish the difference between knowing the name for something and understanding the thing itself. Okay, a lot of people tend to hear inertia and immediately think mass. That's not true. Okay, so that's Newton's first law. And some examples are for seat belts, right? Because you're driving in a car, you're going at, say, 100 kilometers an hour. This means that not only is the car going 100 kilometers an hour, but you are also going 100 kilometers per hour. So if the car were to suddenly stop due to some sort of external force acting on the car, you wouldn't, right? You would maintain your state of motion. It's inertia, right? And therefore we have things like seat belts and airbags to actually bring you to a stop, as opposed to, say, the steering wheel and the windshield. Okay. What other examples do I have here? The headrests are the same thing, right? Except the headrest would be if you're sitting at a red light and someone hits you from behind. Well, your head wants to stay where it is, so it's just going to move back like that, right? As you and the car get pushed forward. That's why you have a seat, but then you also have a headrest back here, also pushing your head forward, right? To prevent things like whiplash. Astronauts placed horizontal for takeoff, same idea, right? You don't want to sit like this as you accelerate upwards, right? Now, of course, your skeletal system is being pushed up by the chair you're in, but what about all of the blood in your body? It's going to want to stay where it is, and so it's going to stay below, and suddenly you lose all the blood in your head, causing you to black out. If you're sideways like this, well, at least you're still going to get blood in the back of your head, which will certainly help keep you awake. All right, so those are different examples of inertia. Now, equilibrium. We say an object is equilibrium if its net force equals 0. Now, that could be two different things. One, it could be there are no forces at all acting on the object, or all the forces that act on the object sum up to 0. Okay, so we say F net equals 0. And although I won't be writing F net in grade 12, I think I've already mentioned this in the previous lesson, I'll be writing the sum of all forces. So if the sum of all forces equals 0, we say the object is in equilibrium and it will maintain its state of motion. Okay, be careful to say that if something has a net force of 0 acting on it, it's at rest. Not necessarily true. Right? Remember, rest is a very relative concept. Right? At rest relative to who? Right? You may be at rest relative to someone, but moving relative to someone else. But in either case, because your motion is not changing, your net force is 0. Okay, so let's go over an example. This is the first example on the back. So here we have a traffic light, and the traffic light is just hanging there. It's just hanging there, its motion is unchanging, therefore we know the net force acting on the traffic light is 0. Now this question says the traffic light weighs 100 newtons, and it's hanging from that complicated cable system shown below. We got 3 cables. Each of them will have a certain tension in them in order to balance the weight of the actual traffic light itself. And our goal, the question is to find what the tension is in those three cables. Now T3 is actually quite easy. So if I drew the traffic light here, and I wanted to know the forces acting on the traffic light. So this is a free body diagram for the traffic light. Let me make this bigger. Now here's our free body diagram for the traffic light. So what forces are acting on the traffic light? Well, there's gravity, or weight. Okay, force of gravity is weight. So we already know that's 100 newtons, because that's what it tells us in the question. And then there's only one cable directly attached to it, and that's T3. Now since it's an equilibrium, we know these forces must add up to 0, so this must be 100 newtons. If you want to see how that looks like in an equation, well, we can just write the sum of all forces, and we can do components, because this is all in y, right, equals 0. That we know. Now what are all of our forces in y? Well, we've got gravity. Let's choose a positive direction. Let's make up positive. Okay, so we have T3. Let's say we don't know what T3 is yet. And then we have gravity, which is acting down, so that's minus 100 newtons, which equals 0. Rearrange the equation, you get T3 equals 100 newtons. Okay, well, that's great. What about the other two cables? Now, the other two cables are actually attached to the third cable. So let's look at that point where they're actually attached. So we have this cable, T3, pulling down. Now why am I writing T3 as being down? In the previous diagram, I wrote it as being up. Well, the tension in a rope, the direction of that force is also, it's an equal and opposite reaction force. And so if I don't have a rope, but let's say I'm pulling on a rope, and there's someone over there pulling the other end. So we're going to imagine a rope here, because I don't have a rope. Okay, now if I'm being pulled this way, I feel like the tension is in this direction, but the other person over here feels like the tension is being in the opposite direction, and it is, right? Remember, for a free body diagram, we're only drawing the forces acting on that object. Well, if we have a tug of war, the direction of the force acting on team A is going to be the opposite to the direction of the force acting on team B. So in this case, the direction of T3 is down, and then we have those other cables pulling in the opposite directions at certain angles, 53 and 37. So 50, this one's 53, and this one's 37. All right, and this one's T1, this one's T2. So our goal is to find the values of T1 and T2. Now we know the whole system is in equilibrium, so we can say things like the sum of all forces equals 0. Okay, but this is in 2 dimensions, so when we're working in 2 dimension, we're going to split things up into components. So we can say this in both the x and in the y components. Now let's write a coordinate system. We can choose this to be positive x and this to be positive y. Doesn't really matter, but you need to stay consistent throughout your question. So make sure you always write it down so that you can refer to it, and on a test so that I can see what you're doing. Okay, now what we need to do is whenever you're drawing diagrams, it's no different from before. This is a free body diagram, but in the first chapter we just drew diagrams. Now on that diagram you're going to have a coordinate system, and any vector that's not aligned with your coordinate system you're going to draw components for. So let's draw components for these vectors. So we have T2. I'm going to put it over here. Okay, where the Z pattern shows us this is 53 degrees. This is our X component and our Y component. Similarly, we can do the same for T1. This is 37 degrees, and this is, we can write it if you like, T1X, T1Y, T2X, T2Y. All right, next thing is to actually look at our equations. Which one would you like to start with? I can't believe I just asked a video which one you'd like to start with. Let's just do x. Sum of all forces in x equals 0. All right, so that's our equation. A lot of times people, students get stuck here, right? They don't know what to do with 0, and they don't know what to do with this. Well, this is the sum of all forces. So we're going to replace this with the addition of all the forces that are in x. So let's just do a little bracket here saying this is going to become all of our x. And how many x components do we have? Well, we have t2x and t1x. t2x is in our positive direction, so I'm just going to write t2x, and t1x is in our negative direction, equals 0. Now I don't need to leave it as t1x and t2x, since I'm not looking for t1x or t2x, I'm looking for t1 or t2. So I can write t1x in terms of t1, right, using our trig ratios, because these are right angle triangles. So t2x I can write as t2 times the cos of 53. t1x is t1 times the cos of 37, which equals 0. But now I truly am stuck, because I have one equation with two unknowns, t2 and t1. Don't know either one. So let's go use our other equation. Sum of all forces in y equals 0. Now how many forces in y do we have? Well, we have t1y, t2y, both positive, and then we have t3. T3 we actually know the value of. It's 100 newtons. So let's write all of these down. Right? So we have t1y, and I'm just going to replace t1y with t1 sine 37. So we have t1 sine 37 plus we have t2 sine 53, which is t2y. And then we have subtract t3, which I know is 100 newtons. And that all equals 0. All right. So now I'm a little bit stuck here. Let me just erase the diagram. We don't need to refer to it anymore. Because again, I have an equation with two unknowns. But I now have two equations with two unknowns. So solve the system of equations. If you like, we can rearrange this one. Let's do that. We can solve for, say, t2. Rearranging for t2, we get t1 cos 37 divided by the cos of 53. All right, we rearranged equation 1 for t2. Now we can take this and substitute it into this equation for t2. And then we'll just have one equation with one unknown. So let's do that. So this is from equation 1. Now subbing that into equation 2, we have t1 sine 37 from here plus t2, but t2 is just t1 cos 37 over the cos of 53. Okay. All times by the sine of 53. And then minus 100 newtons. Or I can write equals and bring 100 newtons to the other side of the equation as a positive value. So now I have one equation with one unknown. Just going to erase these. I'm running out of room again. So we have t1s here that I can factor out. So we have t1 all times by this wonderful trig. Cos 37, so plus cos 37. To make things a little bit less messy, I can take sine 53 over cos 53. Sine over cos, if you remember your trig identities, is just tan 53. And that equals 100 newtons. Now divide both sides by that huge bracket. You can plug things into your calculator and you'll get T1 to be 60 newtons. There you go. Now you can take that 60 newtons, plug it back into this equation, which you solved for T2 in for T1, and you'll get T2 equaling to 80 newtons. Right, so that's how we solve that problem. And we're going to do lots of problems like this. Okay, this net force won't always equal 0. Sometimes it'll equal mass times acceleration, which is from Newton's second law. Newton's second law is a lot to say verbally. It says if the external net force on an object is not 0, the object accelerates in the direction of the net force, and that acceleration is directly proportional to the net force and inversely proportional to the object's mass. Yeah. Oh, we can say F equals ma, right? So we all remember this equation. It's probably the most useful and famous equation in classical physics, where acceleration here is this little symbol here is alpha, and it means proportional to. Acceleration is proportional to net force. What does that mean? That's not an equation. That does not mean acceleration equals net force. It means it's proportional to, so it changes with the same amount of. So if net force doubled, acceleration would double. If net force tripled, acceleration would triple. If net force halved, acceleration would halve, and so on. This one says acceleration is proportional or inversely proportional to mass. This is the opposite. So if mass doubles, acceleration halves. If mass triples, acceleration is reduced by a factor of 3. Okay, but if mass is halved, acceleration doubles. That's where the inverse comes in. So how do you get an equation from this? This you can show mathematically, and we actually did do an experiment in grade 11 with the dynamics carts on the tracks with the pulleys and the weights at the end. We let the weights go and accelerated the cart, and we'd use different amounts of weights and so on. And we'd actually show that these two relationships exist. But then how do you get an equation for that? To get an equation, you put them together and you set them equal, but you can't just set them equal. You need something called a proportionality constant. Why do we have a proportionality constant? We have a proportionality constant because we've created units for these variables. Right? If you simply say acceleration is proportional to net force, it doesn't matter what units you decide for force or what units you decide for acceleration. If one doubles, the other doubles. If one triples, the other triples. The instant you decide to define a unit for force, like newtons, right, and then define a unit for acceleration, like meters per second squared, and define a unit for mass, like kilograms, you have a proportionality constant. Okay, so we have units for mass, the kilogram, and units for acceleration, meters per second squared. So when we write acceleration, when we write this as an equation, we need to put in a proportionality constant to help us equate our units for whatever units we've chosen. So we'd have to write A equals a proportionality constant times F over M. Now if you rearrange this, you get F equals K M A. You might be saying, that is not the equation we did in grade 11. No, it's not. And this is why. We've defined the unit for force to be a newton, and we can't just say, it's going to be a newton. You have to actually define what a newton is. And a newton, 1 newton, is defined as 1 kilogram meter per second squared. Now, if you sub that into your equation, 1, 1, 1, and you solve for k, you're going to get k equaling 1. Okay? It doesn't just equal 1. Right? It has units attached to it. Why did I write equals twice here? It has units attached to it. So this is kilograms times meters per second squared. Okay. So k equals 1 because that'll help us make that into 1 Newton. And since k equals 1, we don't really bother writing it. It's a constant, it never changes. Now, if you use different units, like in the States, they'll say, well, mass is pounds, and acceleration is, they use feet per second squared? Yeah, feet per second squared. Well, then they end up with something they call pounds of force. And they just simply say 1 pound of force is equal to 1 pound times a feet per second squared. But if they wanted their equation to equal a Newton, if they wanted to sub in a pound and then sub in a feet per second squared, then they would need a proportionality constant that does not equal 1. It would have to equal something else in order to spit out units of newtons. Okay? So that's where these proportionality constants come from. And you'll see a lot of them in many of the equations that we use. All right. And that's my spiel on proportionality constants. I also really like proportionalities too. So I could ask on it, multiple choice on it, a test, right? If net force doubles, what happens to acceleration? Okay. Now this leads into, of course, Newton's second law, which, again, we can write in components because our x and y components are mutually exclusive or completely independent of each other. So we can say the sum of all forces in x equals mass times the acceleration in x. Similarly, the sum of all forces in y equals mass times acceleration in y, like so. All right, so let's do the second question on the back of your handout. This one's a lot easier than the first one. It says a horizontal force is applied to a hockey puck. Let me make this bigger. Of mass 0.16 kilograms. Okay. So they give us the mass, 0.16 kilograms. Initially at rest on the ice. So usually when I say ice, it means there's no friction. We'll get to friction later. The resulting acceleration of the puck has a magnitude of 32 meters per second squared. So acceleration is 32 meters per second squared, and I'm just going to write forward. What's the magnitude of force? Ignore friction. So in this case, it's only one force acting on it. So your net force is your applied force. If you were to draw a free body diagram, well, you would have an applied force. It's actually not just one force acting on it. You would also have gravity and the normal force. But there is no acceleration in y, right? All of our forces in y equals 0. So we have an equilibrium in y, right? Because our puck is being launched horizontally. So if we simply analyze the net force in x, that equals mass times acceleration. It would equal acceleration in x, but because there's no acceleration in y, our acceleration in x is our acceleration, right? Because acceleration in y is 0. So that's a lot of explanation just to have this equation. We're just going to sub in numbers, really. That's all we're doing. Okay? I'm not even rearranging it because they give us mass, they give us acceleration. So we have 0.16 kilograms times 32 meters per second squared forward. And put that in our calculators, we get 5.1 newtons forward. Okay, and that would be our net force in x, which is actually just our applied force. All right, so that's Newton's second law, and we will be doing, this is more like a grade 11 problem, but we will be doing more challenging problems in tomorrow's lesson. I'll sort of build them up to make it add a little bit more to each question. So let's go back to the PowerPoint. All right, Newton's third law. Now, this one's really important. It's probably the one everybody remembers, but the one everybody understands the least. It's action-reaction. Okay, it says for every force, there's a simultaneous reaction force equal in magnitude and opposite direction. Now, what I didn't write there, and that is very, very important, is that the action and reaction forces act on different objects. Okay, so let me give you an example. Let's say we had, you might remember this example from grade 11, but it's a good example. Say we had a horse. That's my horse. Pulling a carriage. That's my carriage. I'll give it some wheels and I'll give this some legs. There we go. Horse pulling a carriage. Now, according to Newton's third law, the force that the horse pulls on the carriage is equal and opposite to the force that the carriage pulls on the horse. So how is it possible that the horse and the carriage actually move? Now think about that for a second. If you have to pause the video, okay? If the force on the horse is equal and opposite to the force on the carriage, then it should be in equilibrium. And the net force should be 0 and it shouldn't move, right? Or wrong? All right, so let's actually look at this. The forces are on different objects, and we have to consider the object separately when we want to try and figure out the motion of that object. So let's just look at the carriage. Let's just draw the carriage by itself. Now we know that there's a force due from the horse. Okay. What other forces do we have? Well, we've got gravity. We have the normal force. Anything else? There might be some frictional forces. They're wheels, and we use wheels to try and cut down on friction, so there's probably very little frictional forces. So it looks like gravity and the normal balance, but as long as the horse is pulling at a force greater than the force of friction acting on the cart should move. Well, what about the horse? Does the horse move? Well, we know that it's being pulled back. This force and this force is our pair of forces. It's our action-reaction pair. Right? They're equal and opposite, and they're on different objects. So it is a big force being pulled back on that horse. Now the horse does have gravity, and it does have normal, and those forces again balance, so our net force in y is 0. But is there a force moving forward? You would think there must be, right? Because we know the horse goes forward, so there must be a force forward which is greater than that force pulling it back. So what is that forward force? Can you think of it? It's actually the force of the earth on the hooves of the horse, right? Think of it when you're walking. When you're walking, you push back on the earth and the earth pushes forward on you. Another action and reaction pair. So as long as the horse's legs are strong enough and they can push back on the earth hard enough, the earth will push forward on it. Let's call it F-E for earth. The earth will push forward on that horse. If the horse is not strong enough and can't overcome this action-reaction pair, then yeah, it's not going to move. Okay? So that's how that works. And you can think of, we did lots of examples in grade 11. We did the fan on a boat, right? Trying to hold your own fan to blow the sail. That doesn't work, right? But I'm not going to go over all the examples here. You can think of rockets. Rockets is a great example. Okay? It's why rockets can work in space, because they don't need anything to push off of. They throw something out the back, in this case, very, very hot gases. They expel out the back at very high velocities, and therefore those gases push the rocket forward. Okay, the reason why planes can't work in space is because planes don't have rocket fuel that they push out the back. They have engines that spin and pull in the atmosphere and then push the atmosphere out the back. And therefore the atmosphere pushes them forward. Since there's no atmosphere in space, there's nothing for those engines to pull in and push out. Right? Whereas a rocket expels chemical fuel, right, which is already on board the rocket. Right, now we have one more question to do on the back, talking about weight. Now here's something very, very important. I want to go over some different terms with you. Weight, mass, and the force of gravity. So of those three terms, which two mean the exact same thing? Take a second, think about it. Okay. If you said force of gravity and weight are the same, you're right. So what I want you to do is think to yourself right now what your weight is. Tell yourself in your head, I weigh whatever. Now what I want to ask you is, when you thought about your weight, did you think about it in kilograms or pounds? If you thought about it in pounds, you're wrong. If you thought about it in kilograms, you're also wrong. Right? Mass is defined in kilograms or pounds. Weight and force of gravity is measured in newtons. Okay? Again, it's easy to simply say, oh, weight and force of gravity are the same, but the English language tries to trick us a lot. I mean, you go to the doctors and they say, we're just going to check your weight. Oh, you're whatever kilograms. Like, no, I should be whatever newtons, right? Don't say that to your doctor. They'll get upset with you. All right. So this question says, what is the weight of a 76 kilogram astronaut on a planet where the gravitational field strength is 3.9 newtons per kilogram down? Gravitational field strength, that's another term. Gravitational field strength is the same as the acceleration due to gravity. So if you were to take this equation, Fg equals mg, okay, rearrange it, solve for g, g equals Fg over m. In this case, it looks like g has the units of newtons per kilogram. So g is in the units of newtons per kilogram. But if you were just taking something and dropping it, and you wanted to measure that acceleration, you know that that net force equals ma. Okay, and well, in that case, you would say, well, a is acceleration due to gravity, and we know that that is 9.81 meters per second squared. Well, they're the same thing, right? Even the units are identical, right? If you rearrange this equation, you'll see that a newtons per kilogram are the same units as a meters per second squared. And therefore, whether or not you define something as a gravitational field strength or acceleration due to gravity, you're really talking about the same thing. The reason why we have two different terms is because when we say acceleration due to gravity, we're really more interested in an object actually accelerating in a gravitational field. When we're talking about a gravitational field strength, we're more interested in how strong gravity is in a certain location. Okay, and then if you put mass in that location, it will feel a force. Okay, so you can imagine a field as numbers everywhere around you that describes the field, right? It could describe the strength of the field and its magnitude, the direction of that field, because it's a vector as well. I left vectors off of all of these equations because I'm lazy. Right? And on the Earth, we can say, right, for example, right here, at this point in space, the gravitational field strength is 9.81 newtons per kilogram. So you can say 9.81 newtons per kilogram. And if I were to take an object with mass and put it in that field would cause a force that acts on that object because that field interacts with objects that have mass. Okay? And we can calculate that force using this equation, which we've learned in grade 11. But now what we have is we're on some other planet where the field is actually 3.7 newtons per kilogram down. Now we know the mass. The mass is not going to change. If you go from the Earth to the Moon to Mars, your mass always stays the same. It's the force that acts on you. So your weight is what changes. And we can calculate that weight, or force of gravity, as your mass, which is 76 kilograms, times by the gravitational field strength, in this case 3.7 newtons per kilogram. And you'll see kilograms cancel, and we'll get units of weight, which is newtons. And it's two significant digits, so 2.8 times 10 to the 2, 280 newtons. And down, most likely. All right, so that's it for that lesson. In the next lesson, we're not going to go over any new concepts, but we're going to go over strategies for solving more and more challenging forces problems.